So this is kind of interesting. We have, I don't like to use the word tail with this feature because I think if you use the word tail, the first thing that comes to mind is, oh, it's a comet. And in fact, main belt comets have something that have, several have been discovered in the preceding years. There's something like a dozen main belt comets known now. Active objects in the main asteroid belt, and but I don't want to bias your opinion as to this being a comet. In particular, a comet tail is usually aligned with the direction away from the sun, and in this particular case, the orientation of the sun would be off to the left primarily. So again, if I can get the mouse, well, we'll use this second panel here. The position angle of the anti-sun direction would be about 129 degrees. So north is up, and that would be 0 degrees. East is to the left, that would be 90 degrees. So if you go about 30 degrees past that, or about the 8 o'clock position, this would be the anti-sun direction. So this is the direction you would expect a comet tail if it was an ion tail. Now, dust tails, as you know, can be slightly curved, but the curvature is usually caused by, you know, the particles being pushed away, further away from the sun than the nucleus of the comet, and there they will orbit the sun more slowly, according to Kepler's laws, and so they will start to lag behind the nucleus of the object, and so the tendency is for the dust tail to be sort of spread out into a curved shape, but in the plane of the object's orbit. In this case, the plane of the object's orbit is at a positioning of about 103 degrees. So if this thing was a dust tail, you might expect it to be oriented off in this direction. Clearly, this is off to the south, so it doesn't really match what you would expect for a comet's tail. The other interesting aspect is how long this feature lasted. Scott Shepard was on the Magellan telescope 4 days later and took a very deep exposure, actually 10 exposures with a cumulative exposure time of 2,550 seconds. And again, you can still see a faint extension. The positioning has changed a little bit. Now it's more off toward the southeast, closer to what it would be if it was a comet, but again, we can't discount those Subaru images. And this is also difficult to see, so if you'd like to see it on the laptop blinking, feel free to take a gander after the press conference just to convince yourself that there is a feature there. And there's obviously a lot of light over here on the right. That's just a nearby bright star. And then another few days later, I had some time on the University of Hawaii's 2-meter telescope, and this is a 600, whoops. Can't touch the touchpad. Not much good as a palm rest if you can't touch it. So this is an image of the asteroid again, and really no evidence for any feature present just a week later after the Subaru observations, although admittedly this is not as deep an exposure. This is 600 seconds with a 2-meter telescope, whereas the Subaru exposures were about 300 seconds with an 8-meter telescope. So it just compared the total exposure time there, but there's really no evidence for this feature in the images from 1 week later. And then additional follow-up observations with Magellan telescope in April and May. No feature was visible on those occasions. We also looked through some of the archival images that were available to the public. There's an exposure of Griseldis with the Subaru telescope in 2010 December. No feature visible there. Also 2012 September with the Blanco 4-meter telescope at Cerro Tololo with deck cam. No feature visible in those either. So this is just a crude orbit diagram to show you the location of the asteroid at the various times that I've discussed. The green X is the perihelion location. The red circle is the orbit of the asteroid, 493 Griseldis. The black circles are the inner planets and Jupiter. And the blue circles represent where the observations were made of this asteroid. So the filled circle is where we saw it active in March of this year. The open circles next to it are the April and May observations when it was not seen to be active. The Subaru observations from 2010 are over to the left, and the Blanco observations from 2012 are at the bottom. Again, if you think it's a comet, comets are mostly active when they're close to the sun, closer to perihelion, and these observations are clearly not close to perihelion. So, question is, what caused this feature? Well, there's a summary of some of the things I've already said about position angle of what you would expect for a tail, either a plasma tail or a dust tail. And the position angle we observe is toward the south in the Subaru images. Our preferred interpretation, since it's a single isolated event, as far as we know, but it's worth monitoring. We should go back and keep looking at this guy to see if we might see a repeat event. If there's a repeat, that would make it more likely to be a comet. But if there's no repeat of an event, then it seems to be a single isolated event. It rapidly dissipated as far as we could detect. If we'd taken deeper exposures, even more telescope time, who knows, we might have still found something. Reasonably far from perihelion, and the orientation unlike a comet tail. All these argue in favor of it being an impact event. Now, these sorts of things are not to be unexpected. There's lots of asteroids out there. They do run into each other every now and then. And something should be expected on about 5-year intervals for objects of this size. This is an asteroid about 46 kilometers in size. It has an orbit in the outer part of the main asteroid belt, about 3 astronomical units from the sun. So for objects of this size, you might expect an impact about every 5 years or so. Okay, and next up we'll talk about Churyumov, Gerasimenko. Sonia will tell you about that.
What is Windows? So good afternoon. So I will talk about colors of a comet from the Rosetta observations. As you know, Rosetta is orbiting around the 67P comet since August 2014, and the results I will present comes from the eyes of a spacecraft, the OSIRIS instrument. So OSIRIS is made of 2 cameras, a narrow-angle cameras, which is devoted to the study of the mineralogy of a nucleus. So you have a set of filters from the NAC camera on the bottom, and a wide-angle camera which has a big field of view and it is devoted to the study of the Coma. So the set of data that I will present comes from the first bound orbits. We cover a different phase angle with different filters from the far ultraviolet to the near infrared range. And the images go up to a resolution of 1.3 meter per pixels. So as you may know, the shape of a comet is quite complex, bilobate, and also the morphology is pretty complicated. You have both fragile terrains and rocky consolidated materials, surface covered by regolith, big depression, but also smooth terrains like the happy terrain in the middle between the 2 lobes. So we wonder what's going on colors and composition of the comet with this huge diversity. So first of all, I want to show you the spectrophotometry of a comet. So this is the mean spectrophotometry. You have in this picture, the points are the observation with several filters with the 2 cameras, WAC and NAC. And superposed in gray, it's a ground-based spectrum for comparison. So you may see that there is a nice agreement with ground-based observation globally, and that the spectrum is what we call red spectrum, that is the reflectance increase with the wavelength. And this behavior is compatible with the presence of an organic rich surface as have been seen by the spectrometer on board the spacecraft. This behavior is typical of other primitive bodies like Trans-Neptunian, which are the source of short period comet like the 67P, and unfortunately is tricky to constrain the surface composition because we don't have absorption feature in this wavelength range. So the only one absorption that you may see is in this region, in the ultraviolet, where calibration are particularly difficult. So if real, we interpret this feature as due to the presence of frozen sulfur dioxide, which has also been detected in a gaseous form in the coma of a comet. So we come to the resolved spectrophotometry. So in this figure, you have the spectral slope, that is the difference in reflectance between two given wavelengths, so in the near infrared and in the visible range in this case. So these images comes from observation taken in August 2014 at a phase angle of 50 degrees and a resolution of 2 meters per pixel. And you can immediately see that there are different colors of the comet. So we see heterogeneities in composition, and we distinguish 3 groups of terrains on the basis of a spectral slope. So you have at low in blue in this figure, at medium in green, and high in red the spectral slope. You may see that the blue regions are all focalized in between the 2 lobes, and we interpret this spectral behavior as due to a higher abundance of water ice beneath the surface. And indeed, in that region you have HAPI, but that was the most active region during this observation on the comet. On the other hand, the red regions has been found far away from HAPI. So you see in the picture, they are close to the depression and they are associated to dusty terrains. And interesting, we see the 3 terrains on the basis of the spectral slope in both lobes of a comet, and we do not see color variability between the 2 lobes. And moreover, looking at the stratification within the comet, we see no evidence of vertical diversity in the composition, at least for the first 10th of meters, according to these images. So we also investigate how reflectance vary as a function of the geometry, so on the basis of the so-called phase angle, that is the angle between the sun, the comet, and the observer, Rosetta in this case. So in this picture, you have a nice representation of how reflectance varies with geometry. So going from the top to the bottom, you have, we were approaching to the comet, so the resolution increased, and the phase angle too, and you may see how much the reflectance decrease. And this is due to a combination effect of backscattering and shadowing between the particle in the regolith. So the study of how reflectance varies with the phase angle allows us to constrain some surface composition. And so what we determine is that the surface is very dark. It's like a piece of coal, so it reflects just 6.5% of incoming solar light. We found that the surface is not homogeneous from the reflectance point of view, but there are albedo variations up to 30%. And we found that the brighter regions are also the smoother ones, so happy and Imhotep. So there seems to be a correlation of composition and grain size of the comets. We also do modeling that allow us to constrain the porosity of a surface. So we found that the comet is covered by a porous layer of regolith, and that the porosity we found is pretty high, 87%, and that this value is similar to those of fractal aggregate that are the best analog of cometary dust. So this implies that important processes of dust settling and pulverization are taking place on the comet. So to summarize, we see that the spectrum is red, composition consistent with organic rich surface and similar to that of other primitive bodies, especially trans-Neptunians that are the source of short period comets. We observe both color and reflectance, or albedo if you prefer, variation across the surface, especially in the upper region. We see heterogeneities in composition, and we identify 3 kinds of terrains based on different spectral slope. We see that always on the comet, when you see bluer regions, they tend to be brighter, they tend to become active, and they are and they probably have a higher abundance of water ice. And finally, we found that the comet is covered by a porous layer of regolith with a high porosity value. So thank you. I give the words to the next speaker that will continue on the coma of the comet, always from the Rosetta mission observation. So it's Dennis Bodewitz. Sorry. Oh, here it is. This.
Careful. Thank you, Sonia. I will tell you a little bit about the other camera that is part of OSIRIS. and that are shown here. Sonia just told you about the narrow angle camera. I will tell you about the wide angle camera, which is designed to monitor the Coma. To do this, it was equipped with 14 filters that can sample dust colors and that can also sample different gases. These filters are very specific, very narrow, which in our terminology means that they're only a few nanometers wide. And so you really pick up emission lines, fingerprints of different molecules and atoms. To get you right to the images, here are two of those images shown. What I should first tell you is that to get these images, you need to, those who have a photo camera will notice, this gas is very faint, so you need to have a very long exposure time. And the nucleus is very bright, so what you see is that the nucleus is overexposed, and we sometimes get artifacts on the chip. These artifacts are very well known. The artifacts are shown here on the right of the image, and you see that I blocked it out in one image, and the other image it's not so clear. What you also see here then is a very diffuse emission from indeed oxygen atoms on the left and hydroxyl OH on the right. One of the nice features of the Rosetta wide-angle camera is that you can see those fragments, which are both fragments of water molecules in the Coma, at the same time. And the little cartoon at the bottom shows you what you should see in here. We're starting out with a water molecule, H2O, and there are two different reactions by which you can destroy this water molecule. This is typically done by UV photons from the sun. In one, the water molecule falls up into a hydrogen atom and a hydroxyl radical. That's the lower cartoon here. That occurs at about a rate of a day. The hydroxyl molecule then sits around, is excited by sunlight, and re-emits that light. And what you typically get is an emission pattern that looks like the one in blue over here. The reason for that is that when that hydroxyl molecule is formed, it gets a kick. It gets a kick of about 1 kilometer per second in a random direction, and you end up with what looks like a sphere. The oxygen atom and its light, that works distinctly different. That's a process that we call prompt emission, and that's the cartoon in the top. Water is again destroyed, and oxygen is immediately formed in an excited state, and it immediately radiates when it is formed. And therefore, it traces the water plumes around 67P. And you can see that. There's a strong plume here to the left. I keep getting confused with left and right, so I'm sorry if I get it wrong. And you see that it looks really different from the hydroxyl. So the oxygen atom, it maps directly to water. It's a direct process. The hydroxyl is, there's a certain step there in between. We've been observing this since we first got the Comet. It got, of course, much easier with the Comet getting so much more active. When we first got there, the Comet was only producing a cup of water every second, and that, of course, is a factor of 100 more now. But still, the light that we saw really puzzled us. For whatever reason, we saw 100 times too much light coming from those molecules. Of course, we are very critical scientists. We know this is a tricky instrument. We did our homework. We confirmed that, yes, there has to be a physical reason why this comet is so bright. Now, another explanation for this came from looking at different filters. Another molecule that we can image is a cyanide, CN. And what we saw in this cyanide image is that it looks very much alike the oxygen atoms. Here you have them side by side, cyanide in green, oxygen there in orange. Again, what we know from comets, as seen from Earth, is that cyanide is normally formed in the same way as that hydroxyl emission that I just explained to you. So you start with an HCN molecule, hydrogen cyanide, you hit it with a photon, it's destroyed, you form CN, CN sits around, gets excited, and you would expect a distribution that is spherical, but yet you don't. Instead, what you see is a distribution that looks like the oxygen atoms. And again, as I explained to you, the oxygen atoms, they work differently. They excite immediately when they are formed. So because the morphology, the map of the cyanide and the oxygen is so similar, we concluded that it has to be a similar process that forms it. So this cyanide is formed and immediately emits light. And that's this cartoon what you see here. You have your hydrogen cyanide, and it's formed in CN and H. So cyanide is a prompt emission process. Now, how to explain it then? What we see with OSIRIS are physical reactions that make gas glow. We're not measuring the gas directly. We look at it through light. You got to remember that Rosetta is in a really different position with respect to the comet than when we see them from Earth. We're really close to the nucleus. These images you see were just a few kilometers, 5 kilometers above the surface. And what happens there is that plasma reactions are much more important than photons. So this is a different physical regime where we need to go back to the lab and study those reactions. So what you have are electrons that are formed there in the inner coma, just a few kilometers above the surface, and they hit those molecules and they speed up these reactions by a factor of 100. And that explains why we see so much light and why the light is completely different when you map it than what we see from Earth. And this of course really changes our understanding of reactions in the inner coma. And that was the reason why we went to Rosetta to the first place, to see how to connect what we can see from Earth to what is going on the nucleus. And comet nuclei are normally hidden from sight. One last remark. It's a year ago that we put Philae on the surface, so it's a bit of a birthday party for us from Rosetta. And with that, I would like to give the word to Franck.
So thank you to my fantastic colleagues here. We have been exploring the solar system, so now we're going to use our brain and fly far, far away, still staying in our galaxy, to explore the stars in orbit, the star located at 100 light years away from us. So I'm talking on behalf of the GPIES, the Gemini Planet Imager Exoplanet Survey, which is a large consortium of 85 people from 25 institutions, plus or minus 5. We're all astronomers after all, right? So this is the message. This is a presentation of basically what happened during the first years of the survey. The face of the consortium, so as I said, we have 85 people. We meet every year at different institutions. Here is a picture at Stanford University where our leader, Bruce McIntosh, is located. GPIES, the Gemini Planet Imager, is an instrument which has been developed over a decade. And the goal of this instrument is to be able to image exoplanets. Not every type of exoplanet. At the time we were starting the project, we were focusing on being able to observe Jupiter-like exoplanets, so large, and young, so hot. For this, we developed this instrument, GPIES, here, look on the screen. I don't have a pointer, but here on the screen, which basically is the size of a mini Austin car. He has an adaptive optic system, extreme adaptive optic system, we call it, a coronagraph, and a lot of other instruments to self-calibrate. He's at the Cassegrain of an 8-meter class telescope located in Chile, the Gemini South telescope. So why did we build this instrument? That's not a fancy slide, I know that. The point of our research is to basically understand how we form a planetary system. Because it's embarrassing to say that we still don't know how planets form in our solar system. So one idea is that since we don't understand how planets form in our own solar system, we're going to start looking for planets around other stars. And hopefully, by looking at those planets and understanding the temperature, the compositions, and the distance to the stars, and also the rings of material around it, we could infer the formation of our own solar system planets. So for that, we selected 650 targets. Those are young stars located close to us, typically 30 AU, with an average age of 20 to 30 million years old. And we observed those targets. So in 1 year, we observed 160 targets at the moment. And this is a kind of a portrait of all these observations. In fact, it's 150 of them. These are the type of data we get after processing them. So what you see here, the black spot in the middle is basically a coronagraph that hides the light of the star. And what we're trying to do is to image the surrounding of the star. Okay? The goal is to reach a ratio of a contrast ratio of a million, roughly, at 0.3 arc seconds, typically 3 to 50 AU. So we're exploring the very close area of the star. So we have seen a lot of interesting stuff in these samples already. We've seen disks, background objects. We don't like background objects. They are the vermins of the sky. And some interesting bodies that we don't know, or we're still in the process of analyzing what they are exactly. We call them GOI, GPIES Object of Interest. The interesting body that we announced recently, the discovery of a planet around 51 Eris. So 51 Eris is the 8th type star located 100 light years away from us. And this is an observation we took in December 18, 2014. And this speckle of light here is in fact a planet, a Jupiter-like planet. And what you can see here on the right, it's a spectrum. Okay, we get a spectrum of the planet in J-H-K band, so typically between 1.2 and 2.2 micron, and this is the H part of the spectra. The absorption band you can see on the left and right are due to methane and water. So that's a spectrum which is very similar to a Jupiter spectrum. So the point of my talk tomorrow is basically to confirm that yes, 51 Eri b exists, and yes, 51 Eri b is a planet gravitationally linked with the star. And we know that now because we took another observation in September 2015, and as you can see, we even see the motion of the planet in orbit around the star. So we do have a new spectra, new data. I'm not going to tell much about that at the moment, but we are confirmed now that this is really a Jupiter-like exoplanet in orbit around an F-type star. So it's glowing. It's not an old planet, okay? It's 20 million years old. So what we see is the glow due to the heat during the formation of the planet itself. So from modelings, we estimated the mass of the planet to be twice the mass of Jupiter. And the projected separation, combining all these astrometric observations we get so far, is typically 40 AU. So GPIES has discovered one exoplanet at the moment, but in fact, we often see interesting features around stars, and those are debris disk. Those are secondary products of our campaign. So I could give a talk on each of these targets. I'm just going to show you a few interesting features here. This is a disk, it's AUMIC, M-type star, with a disk here with features inside. This is another disk, HD106906, published by our colleagues Paul Callas, and you can see also the ring disk. And this one is HD131A35, which is a A-type star, large mass, with a disk as well. The disk was imaged with Herschel observation, and now we have been capable of observing it as well in H-band. So what is interesting in those disks is that we see features in it. So we see the rings, and sometimes we see asymmetries. And those asymmetries are most likely due to the formation of a planet, which basically clear the path of the disk of material, or change the shape, or warp the disk. Another interesting body is, of course, Beta Pictoris, and this is a movie we released last month, which is the motion of the planet Beta Pictoris b as it's approaching nearby star. This is a H-on system. So GPIES campaign is underway. We observe only 150 stars roughly. We are going to continue to observe this instrument for the next 2 years at the Gemini South Telescope. We discovered the first exoplanet. It's an interesting body. It's a low mass exoplanet, the first one image, we think. And it's a new field. I mean, we are opening now a new field in the study of exoplanet. We can do finally exoplanetary science. Thank you very much.
All right, we'll open it for questions. Rick has the mic if anybody has any questions.
Rick Lovett, freelance. So this is for Dr. Marchis. What was the smallest exoplanet image before this one?
I don't have the number. I can look on my slide and one of my slides and give you the number. But typically there are 20 Jupiter mass roughly. So this one is really low. It's toward the order of 2 mass of Jupiter. And they're generally hot, much hotter than the one we have. Here we have a temperature of 650 Kelvin. The temperature we get for HR 8799 is roughly 2000 Kelvin. So some people claim that those are not planets. Those are in fact mist stars. And that's why we kind of happy to have this publication of a body that really looks like a planet like we have in our own solar system.
We do have some questions on the webcast, so if there's no other questions from the room, we'll go there. You may have seen a little bit of fuss in the back here. We lost the webcast briefly toward the end of Michael Skrutsky's presentation, and lost just the beginning of Dave Tholen's. But we got the core of your science results, David. But Michael, there were several people on the webcast who asked if you could just go back and explain the light curve, the difference between the incoming and outgoing light curve that you saw during the occultations.
Okay, why don't I
that
just,
got missed.
I'll run up to the podium and do that. Okay, so actually going back to the main animation, you can see for yourself that as the disk of Europa crosses over Loki, the bright volcano, that as it approaches, it sort of cuts up and to the right on the slide. And as it leaves, it's sort of cutting across towards the lower right as opposed to the upper right. And so those two directions are perpendicular to one another. It allows us to reconstruct the image of the volcano. So here it is just in a quick frame-by-frame animation, that I just made up myself. It's not terribly realistic, but here's the ingress when Loki disappears. That's the direction the limb is moving, and I'll jump ahead to the egress. You see it's moving the other way. If you put those two together, I don't know if you can, I hope you can see on the webcast, the circles which define when Loki first began to disappear, when it disappeared completely, when it began to reappear, when it reappeared completely. And you can see how those are oriented relative to one another. And the real punchline is that then you can not only just measure the slopes, actually let me show you the plot briefly again, measure the slopes of the various lines. So here's the disappearance of Loki, and you can see rather than just being a steady descent that it has bumps and wiggles on it. That means you're covering regions of varying brightness as the limb goes across. You have the emergence, same deal. There's information step by step in terms of how much brightness you're covering. Since they are perpendicular to one another, that means that you can put everything together and reconstruct where the bright spots in the lava lake, in Loki Patera, are, and that's on the left on this screen for our occultation observation. It's on the right from when we imaged it directly with the Large Binocular Telescope a year and a half previously. You see the emission is in different places now, and what I said at the very end is this is expected at some level. The position at which the emission is coming from in the lake is going to migrate over time. It may even circulate with a period of about a year and a half, and we see those changes, and the frustration in the end is these are just two epochs and we need many more to make the movie, which we ultimately can do, of this emission moving around. That movie will be made mostly with direct imaging from the LBT because these mutual events have just finished up and Jupiter has to go halfway around the sun again. Before we get them back again, that takes about 5 years. So that was the wrap-up at the end.
Okay, and Kelly Beatty from Sky and Telescope has a question related to what you just went through. Did you get better resolution in one direction, like east-west, versus the other, north-south, as a result of the occultation geometry? And are you able to tell whether the lava lake is the same temperature throughout, or whether it's hotter in different places?
Right. So, yeah, a couple of things there. One is that the rate of the motion of the limb was just about the same in the two directions. So the resolution is about the same, which is between 2 and 3 kilometers per step. Okay, then in some of these events we see steep descent, which means that there are smaller regions that are emitting. And so if you then do the photometry, so you put two things together, you put the size of the emitting region together with the brightness of the emitting region, and from that you can derive crudely a temperature. These things glow like bricks to first order, black bodies we call them in the business, and that's a very simple and direct calculation to estimate a temperature. I have not yet gotten to the point of having enough confidence to do that reconstruction. The maps you see on the screen aren't exactly cartoons, but they are not as quantitative as I'd like them to be at this point. So ultimately, yes, we'll be able to get temperatures region by region on the lake surface. Will we be able to do it on a 3-kilometer scale? I don't think so. You can see the noise in the data. We're probably going to have to smooth over 10-kilometer scales to get better information. But that's still going to be impressive compared to what can be done with direct imaging and compared to what has been done in the past.
Okay, great, thanks. Kelly Beatty has a question for Dave Tholen as well. Can you integrate the dust surface density that you've observed in the collision to estimate the mass lost and therefore the energy of the impact? And can you say anything about the size of the impactor?
All great questions. We've asked those questions ourselves. We would like to do some modeling of the images. We haven't done that yet. That's not been the primary goal of this project, so it's been lower on our priority list. It would be difficult to get a really good answer. We might be able to put like a range of answers on the size of the impactor, simply because this is a two-dimensional image, and to get a good answer, you'd really like to know the three-dimensional structure of this feature. In a sense, it would be easier if it was a comet tail, because then we would have at least a better idea of the orientation. It would be downstream. It'd be in the anti-sun direction, so we'd know it would be going into the screen in those images. If it's an impact event, that material could have come off in pretty much any direction. So we really don't know how it's projected onto the plane of the sky. So that three-dimensional reconstruction is going to involve lots of assumptions, and it's going to be difficult to put a nice tight number on the size of the impactor. So we hope to ultimately put a range of values on it, but I don't think we'll be able to do much better than that.
Can I keep going, Vishnu?
Yeah.
Okay, we have a question from Daniel Fisher for Sonia, and then another question also for Sonia from Kelly Beatty. So first from Daniel, he's a freelancer in Germany. Since there seems to be near consensus in the literature that the comet formed by the merging of two bodies, but you don't see any significant color differences between the two lobes, does that mean that these two bodies were born close to each other?
Well, yes, actually, because we think that there are evidence from layering that the comet is a binary, and we think that it formed very early in the solar system, so from bodies that collide gentle and that were formed in a similar region. So this is one thing, and moreover, it must be noticed that if we see color differences, it will be easier to say, okay, this confirms it's a binary, but if we don't see color differences between the two lobes, we cannot say nothing, because there are a lot of processes ongoing on the comet, so you have a lot of dust settling and transportations, so the comet is covered and resurfaced all the time, so it's really tricky to say from the color point of view that it's a binary or not. But we know that from other studies, so combining other results, that the comet is a binary.
Okay, and Kelly Beatty from Sky and Telescope asked a question about the porosity. You mentioned the very high porosity. He asked if that's due to volatile depletion or due to the gentle backfall of ejected dust back onto the surface, and whether you have any information on the grain size.
Well, on the grain size, not actually. So it's pretty tricky. We do some modeling, and it's there are a lot of parameters. So it's tricky to disentangle all these parameters. So information on the size are given by other instruments, and notably by the lander instruments that are on site. And concerning the porosity, it was just to point out that it's surface porosity, and this implies that there is a lot of void between the grains. And this is typically seen also on other bodies. So we know that when you have processes of pulverization of dust, you have a lot of voids, and especially when you have fragile materials like those expected on the comet.
All right, we'll stick with the comet theme for a minute. A question for Dennis Bodewitz from Kelly Beatty, also from Sky and Telescope. He's asking if you can settle the disagreement over whether the aqua green seen in Comet Coma is from cyanogen or diatomic carbon, or both, and if it's both, does the ratio of those two species vary comet by comet?
Right. So what the question is, indeed, if you see amateur pictures or photographs taken with normal cameras or cameras on telescopes, comets often appear greenish. Other comets appear more white. The emission that I see, cyan again, is actually in the UV. I just called it green because you could tell them apart from my blue hydroxyl emission and the red oxygen. I don't even know. I honestly don't know if we can see it with our eyes, but it's definitely ultraviolet emission. So what you really see is C2, diatomic carbon, And if comets appear whiter, it just means that there's more dust. So the greenish-ness of comets is a measure of the gas to dust ratio of them, which varies from comet to comet.
Okay, and then looks to be the final question at the moment from the web. This is from Ron Cowan, who's reporting for EOS magazine from the AGU. This is for Michael. What's the physics behind the hot spots in loci moving around? How much did the spots move in kilometers or some other measure of distance?
Okay, I'll start this, and I think I'll let Ashley finish it because he's more of an expert. But the whole idea behind the motion of the spots is that as the crustal material cools, it becomes more dense, and eventually it's no longer buoyant and it sinks. So if you can think about a long extended region where that sinking begins at one end, as it sinks, it is replaced by fresh lava, which is hot, and begins a new cooling at that spot. After that happens, the next region over, which presumably this is a cycle, has reached that critical density and critical temperature where it is no longer buoyant, it begins to sink, and you can imagine that process proceeding from one end of the lake to the other and eventually coming back and starting again. And that's the limit of my knowledge and the beginning of my ignorance, so I will let Ashley say a few more words.
Oh, thank you, Mike. Hi, Ron. Ashley Davis from JPL. Been working with, I was invited on by Al and Mike to participate in this very exciting piece of investigation. Yeah, Loki is truly, Loki Patera is one of the great wonders of the solar system. It's a lava lake which, on Earth, lava lakes are just tens of meters across, and here we have something that's 200 kilometers across, and we don't really know what makes it work or why it persists for so long. We have models which predict the different evolving thermal emission signatures from Loki dependent on the style in which the Patera floor, which covers about 21,000 square kilometers, is being continually resurfaced or regularly resurfaced. So what we have here is an absolutely, it's an astounding data set at very high spatial resolution, which will allow us to map out the temperature and area distributions on the surface of Loki Patera and compare this with the predictions from models of different styles of resurfacing. So if it's being resurfaced with lava flows starting at one end of the horseshoe and moving round, you get one temperature distribution. If it starts at the other end of the horseshoe moving in the opposite direction, you get another distribution of temperatures. And if it's indeed the lava lake foundering model, where you have a thick crust on the lava lake, which, as Mike described earlier, thickens with time, reaches a density point, and then sinks, then this would give another temperature distribution, and we can compare this with other observations. We can take what we learned from this and compare it with the integrated thermal emission spectra from lower spatial resolution observations with other instruments. We can compare it with data collected from spacecraft, such as the Galileo spacecraft. And I'm very excited about this because this could really give us a good handle on really getting down into the nuts and bolts of what makes Loki Patera, this massive volcano outputting 10 terawatts on average, what makes this thing work.
Okay. Any more questions in the room? Okay, with that we'll wrap up.
Wait.
Oh,
Sorry. One more question came in on the web. This is from Kelly Beatty for Sonia again. Can you describe the plans that the team may have for doing more spatially detailed spectra as Rosetta descends closer to the comet next year? Like, are there any specific targets?
So we already have
after?
a lot of highest resolution images that we will analyze. So as you may know, Rosetta will land on the comet in September 2016. And the plan is to do as much as possible compatible with the life of the instruments. So we will take images in different filters to constrain the mineralogy and local variation during the descent. And when we will get very close, probably we will get images only in one filter to get the higher spatial resolution as possible. This is the preliminary plans, but of course we have to deal with orbits and many other parameters, so we hope that the instrument will stay alive and work properly as it does up to now.
Okay, there are no more questions online.
Okay, any questions in the room? Okay, with that, we'll wrap up all the press events, and I'll see you guys in Pasadena next year. Thank you.
Thank you, Ashley.